Hello everyone, welcome back to Neural Networks Explain Part 10, and today this is going to be a long video about backpropagation. Let's get started. So, as a recap, we have seen that given a pair of input and output, we can calculate a cost function that only depends on the weights and the biases of the neural network. We've also seen that we want to minimize the cost function. That is, we want the value of the cost function to go down. And finally, we know that we can minimize the cost function using gradient descent. And how do we do that? We just need to calculate del C over del W, that is the partial derivative with respect to the weight, for each weight, as well as del C over del B, so the biases, for each biases. So the formulas for feed-forward, if you refresh your memory a bit, were that Z of n is equal to the weights, the matrix weights of the previous layer, multiplied with the inputs of the previous layer, matrix multiplication, plus the biases n minus 1, and then we would have to activate this, so ReLU of this, and it would give us x of n or a of n, which can be used interchangeably. And if we put everything together in one big expression, we have that x of n is equal to ReLU of the weight matrix multiplied with the input vector from the previous layer plus the bias. So now we are going to be using the chain rule to calculate the partial derivatives we need. So recall that the chain rule for a single variable calculus for something like f of g of x was that df over dx is equal to df over dg times dg over dx. And again, the intuition is that you can cross them out like this. So this crosses out, something like that. And in multivariable calculus, we have to make sure that we cover each possible path from f to x when calculating the chain rule. So for example, given an expression f of g of x, h of x, that is f is a function that accepts two inputs, g of x and h of x, then we have that df over dx is equal to del f over del g times dg over dx plus del f over del h times dh over dx. So why is that? As you can see, there are two paths that from x goes to f. So there is f that goes to g of x, and that goes to f of g of x, and something else. There's also x that goes to h of x, which goes to f of something, then h of x. So when we're doing the chain rule, we just need to make sure that we cover all paths from x to f when using the chain rule. So this is the first path, you go to x, g, then f, so this gives us del f over del g times dg over dx, so you can think of it that it simplifies it, and then you have del f over del h times dh over dx, that is the path from x to f using the function h. And this again, you can think of it as it's going to cross out, and this in the end gives us del f over dx plus del f over dx, but more precisely del f over dx by passing through g plus del f over dx by passing through h. Nice. So we are now going to look at the cost function. So if you remember correctly, the cost function was that it was the cost function of something expected, then predicted, and it would just be the absolute value of the predicted minus expected. There are also different values of cost function, but you'll see why we're going to be using this particular one, the mean absolute. So we want to be able to derive this function. So what I'm going to do is that I'm going to calculate del C over del A. That is, I have this function, which is a absolute function, and then you'll see that when it's above 0, I have a slope of 1, and when it's below 0, I have a slope of -1. But what is going to be above 0 and what is going to be below 0? It is the expression in the absolute value, so a minus y. So I'm going to define a function called sine of x, which is going to be -1 if x is smaller than 0, and 1 if x is bigger or equal than 0. So then I can finally have del c over del a is equal to sine of a minus y, and this makes sense. Why? Because when a minus y is smaller than 0, you see that any points here have a slope of -1, and then you see that here when a minus y is bigger than 0, any point here has a slope of 1. So this is pretty awesome. So let's make an example. Let's say I have a is equal to 0.5, y is equal to 0.3. Then I have that the cost of ay is equal to the absolute error of 0.5 minus 0.3. Because 0.5 is predicted, y is equal to 0.3 expected, which gives us 0.2 absolute value that, and that gives us 0.2 again. So we have that del c over del a is equal to sine of a minus y, and that sine of 0.2 is equal to 1. So this is still correct. So if we had multiple outputs, then we would have an output vector. So let's say I have an output vector which is 0, 0, 1. So this is what I'm expecting. And then I have a prediction, and that's going to be 0.1, 0.2, and 0.7. Then I have that the cost of this is going to be this expression, which is basically just you have the absolute function, and you put the vector y minus the vector a, and you sum each element, and then you divide by the number of elements. So if I rephrase it, then it means that you take the vector y minus the vector a, absolute value that, and you take the mean of elements. So this is going to give me 1 over 3 because there are 3 elements times the sum of absolute value of 0, 0, 1 minus the vector 0.1, 0.2, 0.7. This will give me 1 over 3 times the sum of the vector minus 0.1 minus 0.2, 0.3. And then I put absolute value, and I have 1 over 3 times the sum of 0.1, 0.2, and 0.3. This gives me 1 over 3 times 0.6, which gives me 0.2. Then I can calculate the partial derivative. So del c over del a, but the vector a, so this is going to be just del c over the vector a is going to be a vector comprised of del c over del a1, del c over del a2, del c over del a3, and so on and so forth. I have, this is going to be sine of a minus y, and again, it's not going to change, which gives me sine of this difference, which was minus 0.1, minus 0.2, 0.3, and this is equal to minus 1, 1, because minus 0.1 and minus 0.2 gives minus 1, since it is smaller than 0, and 0.3 it's bigger than 0, so this gives me 1. So now, we've managed to calculate del c over del a, and more precisely, del c over del a of n minus 1, so del c over del a of the last layer, where n minus 1 refers to the last layer. So we now want to calculate del c over del z, n minus 1, the vector z, by the chain rule, and we know that del c over del z n minus 1 is equal to del c over del a minus 1, and this is going to be an element-wise product, so I'm going to put a circle around it, and then element-wise product with del a, vector del a, n minus 1, then del z, vector n minus 1, and you're going to see why it makes sense. So we know that del c over del a n minus 1 is equal to sine of a minus y, as we just showed, and that a of n minus 1 is equal to ReLU of z n minus 1. And if you look at ReLU, when x is smaller than 0, we have a slope of 0. And when it is bigger than 0, we have a slope of 1. So I'm just going to define a function called step, which is going to be 0 if x is smaller than 0, and 1 if x is bigger equal than 0. So we then have that del a over del z is equal to step of z n minus 1, because as you can see, the input passed is going to be z. In the ReLU function, you see that the input is z. We also see that the step works because when it's smaller than 0, it's 0, and when it's bigger than 0, it's 1, the slope. So given an example, let's say I have z n minus 1 is equal to minus 2, 3, 1. I do the ReLU of that, and I get 0, 3, 0 as activation. Then I will have del a n minus 1 over del z n minus 1, which is equal to step of z, the vector z, n minus 1. And this is equal to step of minus 2, 3, minus 1. As you can see, this is z here, z is also here. And this gives me 0, 1, 0, because minus 2 and minus 1 are smaller than 0. So combining del a n minus 1 over del z n minus 1 and del c over del a n minus 1, we have that del c over del z n minus 1 is equal to del c over del a n minus 1 times the element-wise product of del c over del z n minus 1, which is just sine of a minus y with the element-wise product of step of z. So that was the chain rule. It makes sense again. So as you can see, the chain rule is that you can have these vectors and it is going to be annihilated. So this is going to be del a n minus 1 and it's going to cancel out. So for an example, let's say I have y is equal to 0, 0, 1, and then z n minus 1 is equal to minus 0 0.2, 0 0.3, 0 0.7. Then I will have that a n minus 1 is equal to ReLU of that, which gives me 0, 0, 0 0.7. If I want to calculate the cost of this, I will have all this blah blah blah, so the mean absolute error, and it's going to be give me 0.1. You can calculate del c over del z n minus 1, and this is just the element-wise product of del c over del a n minus 1, element-wise product with del a n minus 1 over del z n minus 1. And why does the element-wise product make sense? That's because you're just going to be matching a n minus 1 with a n minus 1. So these are going to multiply together, these are going to multiply together, these are going to multiply together. And in the end, you would think of it that, for example, del c over del z1 n minus 1, this is just equal to del c over del a n minus 1, 1 times del a n minus 1 over del z n minus 1, 1. So this makes sense. And this is just going to be an element-wise product because, as you can see, this is just the first element in the first vector and first element in the second vector. So let's continue on, and we have that this is going to be sine of 0, 0, 0 0.3 element-wise product with 0, 0, 1. So 1, 1, 1 is 1 element-wise product with 0, 0, 1. This gives us finally 0, 0, minus 1. Now we'll get to the fun part. We're going to derive what are actually useful. So the biases, for example. So we will now calculate del c over del b n minus 1. And we know that del c over del b n minus 1 is equal to del c over del a n minus 1 element-wise product with del a n minus 1 over del z n minus 1 element-wise product again with del z n minus 1 over del b n minus 1. And why? You can think of it as because it's just going to use the same a and the same z. So z1 to a1 to c. So b1 to z1 to n1 to a1 to c. Voila. And we also know that z is equal to wx plus b. So in other words, z is a vector that's going to be b1, b2, b3, b4 plus wx. Or z1 is equal to b1 plus the first element from that matrix multiplication. z2 is equal to b2 plus second element of the matrix multiplication. z3 is equal to b3 plus the third element of matrix multiplication. And z4 is equal to b4 plus the fourth element of the matrix multiplication. And we're just going to take 1 to analyze it, and we see that if you want to take del z1 over del b1, this just looks like a linear equation. So this is a constant, and this is just something with a slope of 1. So there's an imaginary 1 here. And thus, we have that del z1 over del b1 is equal to 1. Del z2 over del b2, it's the same logic, it's also going to be 1. then del z3 over del b3 is also going to be equal to 1, and del z4 over del b4 is also going to be equal to 1. Thus, I have that del c over del b n minus 1 is equal to del c over del a n minus 1 element-wise product with del a n minus 1 over del z n minus 1 element-wise product with del z n minus 1 over del b n minus 1. And then, as you can see, since this is just 1, 1, 1, 1, 1, 1, as we've just seen here, del z1 over del b1 is 1, del z2 over del b2 is 1, and so on and so forth, we have that del c over del vector b n minus 1 is just equal to del c over del a n minus 1 element-wise product with del a n minus 1 over del z n minus 1, because multiplying by 1 to each element is going to do nothing. So this is awesome. We now know how to update the last bytes correctly. So that just means that we're going to take this and then subtract this from the biases. So let's calculate the weights now. So we know that z is equal to z1, z2, z3, and that it's going to be a vector. If you expand its form, it's going to be w11 x1 plus w12 x2 plus w13 x3 plus b1. And just a quick tip for the weights, the last index is always going to be matched with the same index from the input, and the first index is always going to be matched with the index of this output. So let's calculate, for example, del z over del w22. So where does w22 appears? And we see that the first time that it appears, it is just in the second row, in the second term, so w22 x2. And since these are just going to be constant, this and this becomes the only term with w22, and what is the slope of it? It's going to be x2. So del z over del w22 is of x2. More precisely, you could say that del z2 over del w22 is equal to x2, but this doesn't really change anything because these are irrelevant. They don't contain any w22 and it does not affect us. Finally, we have that del z2 over del w32 is equal to x2, del z2 over del w21 is equal to x1. So this is going to actually be del z3 over del w32, because as we can see, this belongs to the third row, w32 is here, so in the third row, and this is going to be x2, and we can continue with that. Now, what is del c over del wij? It is just going to be del c over del zi times del zi over del wij. As you can see, the chain rule is still here. It's stack. It gives us del c over del wij, which is what we want. So we also know that del zi over del wij is just going to be xj, and we can substitute that, and we get that del c over del zi times xj. We can now construct the matrix of partial derivatives, so del c over del matrix w, and this is just going to be the partial derivatives of each weight. So this is going to be I equals to 1, I equals 2, I equals 3, I equals 4. This is going to be j equal to 1, j equal to 2, j equal to 3, and j equal to 4. And then, as you can see, here we have I equal 1, j equal 1. We take the thing we found here, so del c over del z1 times x1. This becomes, as you can see, it becomes what we want. And as you can see here, let's say that we had a certain I and j, then it's just going to be del c over del wi xj. Here, as you can see, it's going to be del c over del z1 times x4, because I is equal to 1 and j is equal to 4. And these here, I didn't write it, but you can see that it's going to be del c over del z2, del c over del z3, and all that. So this is going to be del c over del zi, whoopsie doopsie, and we can now continue. So it's always going to be del c over del z, and the matrix can be represented by the result of a matrix multiplication. So if you look at it, we see that it's going to be a vector del c over del z1, del c over del z2, del c over del z3, del c over del z4, multiplied with a vector like this. It's going to be x1, x2, x3, x4, And as you can see, it's going to give us what we actually want. For example, here, we're just going to do this times this, and you can see that it gives us del c over del z1 times x1, which is what we want here. And for example, here x3, and then del c over del z2, it gives us del c over del z2 x3. And this is also what we want. So this is actually very nice. So therefore, del c over del w, the matrix, it's going to be equal to del c over the vector del z. So this thing here, matrix multiplied with this thing here, and this is just the input from the previous layer transposed, because usually vectors are vertical. To make it horizontal, you're just going to make it a transpose. So del c over del z time matrix multiplied with their transpose, and comes, for example, to a vector 1, 2, 3 like this to 1, 2, 3 like this. So as a recap, we have seen that del c over del b is equal to del c over del a element-wise product with del a over del z, and then del c over del w, the matrix, is equal to del c over del z matrix multiplied with the transpose of x. And if you can expand it, you see that it gives us del c over del a vector element-wise product with del a over del z, then matrix multiplied with x, the transpose. We now need to calculate del c over del a n minus 2, so we can use the chain rule to get del c, del w n minus 3, and del c over del b n minus 2. So remember that z is equal to wx plus b, so we can actually expand it, and we'll get that z is equal to w11 x1 plus w12 x2 plus w13 x3 plus b1. The second row is going to be the same thing, so w21 x1 plus w22 x2 plus w23 x3 plus b2, and then w31 x1 plus w32 x2 plus w33 x3 plus b3. And we can see that if we want to calculate del c over del x1, for example, then we need to add multiple chain rules together, because there are multiple paths going from x1 to c. So as you can see, there is the x1 in the first row, so x1 to z1 to c. We also have x1 in the second row, so x1 to z2 to c, and the same thing in the third row, so x1 to z3 to c. Therefore, del c over del x1 is equal to del c over del z1 times del z1 over del x1 plus del c over del z2 times del z2 over x1 plus del c over del z3 times del z3 over del x1. And notice that del z1 over del x1 is simply w11. Why? Because as you can see, this is just a constant, because it doesn't have an x1, and the one with the x1 has a slope of w11. We also know that del z2 over del x1 is simply w21, so same logic applied. So w21, and then this is going to be constant, so w21 is in front of the x1, so this is the slope. And in general, del zi over del xj is simply wij. So del c over del xj, for example, it's going to be equal to del c over del z1 times del z1 over del xj plus del c over del z2 plus del z2 over del xj plus del c del z3 times del z3 del xj. We finally have that again. This gives us del c over del xj, which is equal to del c over del z1 times w1j plus del c over del z2 times w2j plus del c over del z3 times w3j. We can now express that in a matrix, or a vector more precisely. So del c over del x, the vector, is going to be equal to del c over del z1 times w11 plus del c over del z2 times w21 plus del c over del z3 times w31. The second row is going to be del c over del z1 times w12 and all that. I won't go and say everything. And this can be represented as a matrix multiplication. So let's say I had my weights like this. So w11, w21, w31. So the transpose of the weights technically. And then I would have another vector on top, which is del C over del Z1, del C over del Z2, del C over del Z3, which is just del C over del Z, the vector, we can see that this is going to give us what we actually want. So let's make a multiplication, for example. So I'm going to take the first row, take the first matching element. This is going to give me this product plus this, which gives me this product, and then this, which gives me this product, which is also what we want because, as you can see, this is the same thing as here. So this looks like the weight matrix, this looks like the weight matrix, but it's actually the weight transpose. So these are the original weights, W11, W12, W13, but here it's W11, W21, W31. So I and J are swapped. The first index and the second index are swapped. So to re-swap them back, we know that it's just going to be a transpose. So this is just weight transposed. We then have that del C over del X, the vector, is equal to the weight transposed matrix multiplied with del C over del Z. And now we have learned everything there is to backpropagation. So first, given an input and output pair, we feed the input to the neural network. Then we calculate the value of the cost function. So we calculate del C over del Z n minus 1, which is just going to be sine of a n minus 1 minus y, element-wise product with step of z n minus 1. So this is going to be calculated later after we calculate the cost function. Now we can calculate del C over del B n minus 1, which is just del C over del Z n minus 1. We can now do gradient descent. So we're going to take B n minus 1, and then we're going to subtract del C over del Z n minus 1 times a certain learning rate to scale it down. So to make sure the steps you take are not going to be so drastic. We're now also going to calculate del C over del W n minus 1 n minus 2, which is just equal to del C over del Z n minus 1 matrix multiplied with the transpose of a n minus 2. Gradient descent again. We're going to take W n minus 2 and subtract del C over del W n minus 2 times the learning rate. Now we're going to backpropagate. So we're going to calculate del C over del A n minus 2. So the one before the output layer, which is just going to be W n minus 2 transposed times del C over del Z n minus 1. With this, you can calculate del C over del B n minus 2 because this del C over del B n minus 2 just equal to del C over del Z n minus 2, and this is just equal to del C over del A n minus 2, element-wise product with step of Z n minus 2. And we then have that del C over del W n minus 3 is just del C over del Z n minus 2 matrix multiplied with A n minus 3 transposed. Gradient descent again. So for B n minus 2, we subtract del C over del B n minus 2 times a learning rate. And then for W n minus 3, we subtract del C over del W n minus 3 times a learning rate. We can now calculate del C over del A n minus 3. So this is just another step for that backpropagation. We're going to calculate the gradients for the layer before. So this is going to be W n minus 3 transposed times matrix multiplied with del C over del Z n minus 2. So we repeat again, del C over del B n minus 3 is just equal to this. As you can see, it's just nothing special. Del C over del A n minus 3 element-wise product with del C over del Z n minus 3, which gives us step Z n minus 3 element-wise product with del C over del A n minus 3. And finally, we have that del C over del W n minus 4 is just equal to del C over del Z n minus 3 matrix multiplied with A n minus 4 transpose. We do gradient descent again, and we then have that B n minus 3. We can subtract del C over del B n minus 3 times the learning rate. We have W n minus 4, and we can subtract del C over del W n minus 4 times the learning rate. And we're just going to repeat backpropagation with this formula. We're going to repeat until the first layer, and you're going to update all the weights and all the biases. Once this is done, this means that you have successfully learned all about backpropagation. And in the next video, we are going to look at how we can implement it in Python, and you can see the code is much easier than this. Thank you so much for watching. That was a very long video, and if you like this content, like, subscribe, do all that good stuff. And in the next video, we're going to be looking at implementing the neural network in code using Python and NumPy. So stay tuned.